My name is Vadym Doroshenko. I'm from Google anonymization team. My team is working on anonymization infrastructure for Google, and especially for differential privacy. This is our focus. And today I'm talking about utility analysis for differential private pipelines. And this is our latest project. This is part of PipelineDP project. So my plan for today is to talk shortly about PipelineDP, then to provide example and to show why utility is complicated on this example, and explain our approach to that. So let's start with a quick recap of what is PipelineDP. So PipelineDP is for doing anonymization with differentially-privacy. And this is a Python library for distributed computations, for computing basic differentially-private aggregations, such as count, sum, quantiles, and so on. And it's open sourced. You can check it on PipelineDP.io website. And this is a joint project between Google and OpenMine privacy community. And PipelineDP is designed for a wide audience, which includes, of course, non-DP experts. And while DP is a very nice mathematical framework, there are many challenges with usability, especially for non-experts. And for this talk, let's discuss two of these challenges. One of them, for any person who would like to use it, what would be the hyperparameters and for these computations? When we choose some hyperparameters, what would be the impact of computations, DP computations on utility? And let's illustrate these complexities and hyperparameters for one simple example. So let's take some fake dataset, synthetic dataset, which contains visits for restaurants. So let's say it's a table with 3 columns: visitor ID, some restaurant, and day of week. So it's visits of restaurants for 1 week. And imagine that we'd like to compute for this simple dataset how many visits per different days of weeks. And we'd like to do this with differential privacy. And the classical way to do it is to apply a Laplace mechanism. So how can we do this? Let's compute count of visits per Monday, Sunday, and for all days, and let's add Laplace noise. And in pseudocode, it can be something like that, that we take count for Monday, and we add Laplace, random variable for Laplace distributions, and this will be a differentially private count. But here, one thing is that we need to have L1 sensitivity in Laplace, as it's in theory. And what is L1 sensitivity? So let's just consider for this case, this is, in general, sensitivity is something that we need bound sensitivity of query in order to protect each user. So it's how much the query before differential privacy changed by adding 1 user. And in this case, L1 sensitivity is simply the maximum number of restaurant visits per visitor. And wait, what would be the value of L1 sensitivity in this case? One visitor can visit restaurants many times, and if you choose this like number very large, we need to add a lot of noise. So we need somehow bound this sensitivity. And PipelineDP solution is to do contribution bounding, which is sampling per visitor. And this is where we have additional hyperparameters. We need somehow to specify sampling, how to perform sampling. And it's chosen in PipelineDP. It's controlled by 2 parameters. This is how it's called in PipelineDP, max partition contributed. In this case, this is in terminology of PipelineDP, partition is day of week. So this is max partition contributed means how many days one person can go to a restaurant in our dataset. And another parameter is max contribution per partition, which means how many times per day one person can go to restaurants. And advanced sensitivity in this case would be just product of these two. And it's easy to see, for example, if the first one is 3, so it means maximum 3 days, and the second is 2, maximum 2 times per day, then maximum it will be 6 like product. So we have, that way we introduced 2 hyperparameters. And if we'd like to compute counts proper way with differential privacy, we need somehow to choose them. And of course, we'd like to choose it somehow that the DP output would be close to the actual output. So let's, for example, illustrate what would be with bar chart plots. What would be if we choose too low contribution bounding. So this is like blue one is row count and orange one is output with DP. And for example, if you choose this contribution bounding is too low, we will have, then it means sampling will be very aggressive and a lot of data will be dropped. And basically it introduces a lot of statistical bias in the output. On the other hand, if you choose these parameters high, then sampling will be almost no operation, but Laplace noise will be high. And essentially, we have bias variance trade-off here. Then let's, for simplicity, consider only one parameters. And if we choose this, it's higher. Contribution bounding error will be smaller. And typically, it looks like that. And Laplace noise, of course, goes higher. And if you combine that, usually it looks like that. So there is somewhere minimum, which it would be nice to have at least close to the minimum. And let me emphasize that the contribution bounding error is choosing this parameter, and contribution bounding error is data dependent. Well, Laplace noise is, of course, depends only on this parameter. Yeah, basically this is the thing that we need to somehow to find these parameters. And our approach to this problem is we call it analysis framework. That it suggests parameters. It takes dataset and suggests parameters. And it provides error estimation for suggested parameters. So let me emphasize that this is the output of analysis framework is not differentially private. And usually it's what clients want. They want to understand with certainty that DP works or doesn't work. And that's why it's not differentially private. But it means that output should be treated with care, and it should be published. And high level, it works like following: that there is utility analysis part, that that for each computations, DP computations, there is like some computational graph, which is like some pipeline, computing pipeline, and it has some nodes corresponding to like sampling, to noise, and some others. And analysis framework uses the same computational graph, but it replaces nodes which correspond, for example, to sampling with nodes that correspond to modeling of sampling, which computes error, and the same with noise and others. As a result, for each of hyperparameters configuration, we can estimate error with some error metric. And the second part is when we already have utility analysis. Second part is parameter tuning. So let's basically how to minimize function of a few variables, but the main challenge is that computing once this function is expensive because usually the data set's large. Yep, and this is how it looks like. So there is a demo on GitHub in Google Colab. This is basically to illustrate how it works. So imagine that we have functions that do computations implemented with PipelineDP for computing counts that takes data, some DP budget, let's choose some reasonable DP budget, and some hyperparameters. So, and of course the question what would be how to choose these hyperparameters. And there is a function run analysis that it takes data and it takes budget. So budget is fixed. So here is the question only how to choose beta parameters better. And in case of this demo, it returns something like that. So there are some fixed parameters. For example, for this synthetic data set, max precision contributed is the best one is 4. And let's illustrate on these charts which were previously when lot of bias, lot of variance, and this is what analysis framework returns. So in this case, DP output is very close to the actual output. Next steps for this project. So as I mentioned that it's open source, all implementation is algorithms on GitHub. And so PipelineDP can run on, in order to make distributed with different frameworks like Apache Beam or Apache Spark. But there are some requires connectors for infrastructure to make it sure that it works with Apache Spark. And another things that we found it's pretty complicated, like how to convey results to the clients. And how convey to the result to non-experts because DP is complicated and different people interested in different metrics and so on. This is things to do. And and I encourage you to try it on try demo in Colab. So you can go to demo from PipelineDP.io website. And you can open demo in Google Colab and to run everything. So, and if you have any questions, so please connect us for DP by dp-open-source at google.com. If you have questions about how to use framework or you'd like to try, and so we will try to help you. Or you can connect me directly by this email. So thank you very much for attention.